Hello students, today we will discuss the numericals of diffraction. First, let us quickly see the formulas. Intensity due to single slit is given by I is equal to A square sine alpha by alpha whole square, where A is the resultant amplitude. Position of minima due to single slit is given by A sine theta equal to plus minus n lambda, where A is slit width, n the order of the minima which you are going to take, lambda the wavelength. For secondary maxima, A sine theta is equal to plus minus 2n plus 1 lambda by 2. The width of central diffraction maxima is given by 2 into focal length into wavelength divided by slit width. Let us begin with the numericals. Now, light of wavelength 5500 angstrom falls on the slit of width 22 into 10 to the power of minus 5 centimeter. You have to find the position of the first two minima on either side of central maxima. The angular positions of the minima in a single slit diffraction pattern are given by A sine theta is equal to plus minus n lambda, where n is 1, 2, 3. Now A has been given as 22 into 10 to the power of minus 5. Lambda is 5500 into 10 to the power of minus 8. For first order minima, n will be equal to 1. So sine theta 1 comes as this much. For second order minima, n equal to 2. And the first two minima will occur at angles 14 degree 29 minute and 30 degree on either side of the central maxima. Light of wavelength has been given to you is incident on normally on a single slit. Central maximum falls out at 30 degree on both sides of the incident light. You have to calculate the slit width, and for what width of slit the central maximum will spread out at 90 degree from direction of incident light. Now in Fraunhofer diffraction due to single slit, direction of minima is A sine theta plus minus n lambda. Angular spread of central maxima on either side, sine theta equal to lambda upon A. So A, the slit width, is equal to lambda upon sine theta. We put the values that have been given. We have changed angstrom into centimeter and we get the answer. For theta equal to 90 degree, A is this much. Next, light of wavelength has been given to us as incident normally on a slit. First minimum of diffraction pattern is observed to lie at a distance of 5 millimeter from the central maxima. From the slit, calculate the width of the slit. In Fraunhofer diffraction, single slit is formula is A sine theta plus minus n lambda. Now, angular separation between first minima on either side of central maxima is A sine theta equal to lambda. So sine theta is lambda upon A. If theta is small, sine theta tends to theta. So theta becomes equal to lambda upon A. Linear separation between the first minimum and central maximum is 5 millimeter, that we change into centimeter. So distance of screen from slit is given as 2 meter, which is 200 centimeters. This is where the central maxima comes, followed by secondary maxima and minima on other side. This is the slit width A. This is the distance 200 centimeter that has been given to you. Straight away put the values in the formula and you get the answer. Fraunhofer diffraction due to narrow slit, a screen is placed 2 meter away from the lens to obtain pattern. If the slit width is 0.2 mm and first minima lies 5 millimeter on either side, find the wavelength of light used. So here in this diagram, you can see central maxima, first minima, angle, slit width. So A sine theta is plus minus n lambda. You put sine theta as n lambda by A. If theta is measured in radians, then for small values, sine theta tends to theta. So theta becomes equal to n lambda upon A. Angular separation between first minimum on either side of the central maximum is theta equal to lambda upon A. For n equal to 1, A is this much. In radians, theta is lambda upon 0.02 radians. And distance between the first minimum and central maximum is 0.5 centimeter. Taking triangle OPC from the figure. We have a look at the figure. OPC, this triangle we have taken, we get the answer CP upon OC is equal to 0.5 divided by 200 radian. Comparing equations 1 and 2, lambda, we get for theta, this is this and this, we get the answer. Plane wave of wavelength falls normally on the slit of width this much. Calculate total angular width of the central maximum, linear width of the central maximum on a screen placed 2 meters away. So see, direction of minima is given by this. For first order, n is equal to 1. So a sine theta lambda, sine theta is lambda upon a. When theta is small, sine theta tends to theta. So theta becomes lambda upon a. You get the answer. This is the angular half width of central maximum. Total angular width of central maximum 2 theta because it is formed on either side. Linear half width x is equal to theta d. We have explained in the previous numerical. So it becomes 2 into theta d and you get the value. Calculate the angle at which the first dark band and the next bright band are formed in the Fraunhofer diffraction pattern, and the slit width has been given to you. In Fraunhofer diffraction, direction of minima is given by this. For first dark band, n is equal to 1. So a sine theta equal to lambda, sine theta is equal to lambda upon a. The angle of diffraction corresponding to first bright band on either side of central maxima is this much. So lambda is this, sine theta is this, theta is sine inverse this much. A single slit of width is given, is illuminated by monochromatic light. Diffraction bands are observed on the screen 2 meters away. If the center of the second dark band is 1.6 centimeter from the middle of the central wide band, reduce the wavelength. Central maximum is exactly midway. Therefore, distance of first minimum from central maximum is this much. Theta is x upon d. A sine theta is plus minus n lambda. All this has been done in the previous numericals. Put the value of theta a, what you have been given in the numerical, and you get a. A single slit of width 0.14 millimeter is illuminated normally. Find if the center of the second dark band is 1.6 centimeter from the middle of the central wide band, reduce the wavelength of light. Sine theta is n lambda. For theta small, sine theta tends to theta. Theta is n lambda upon a. We have been given the values. First diffraction maximum and coincide with the first minimum of red light of wavelength this much. This I will explain you in detail right now. A single slit is illuminated by light composed of two wavelengths. One observes that due to Fraunhofer diffraction, the first minimum obtained for lambda 1 coincides with second diffraction of lambda 2. What is the relation? For second n equal to 2, equating the two equations, that's the answer. In obtaining the diffraction of a single slit, the focal length of lens used is 100 centimeter and the width of the slit is so much. Find the width of central maxima. Width of central maxima 2r equal to 2f lambda by a. F is 100 centimeter, lambda is 4500 angstrom, a is 10 to the power of minus 2 meter. Calculate the wavelength of light whose first diffraction maximum in the diffraction pattern due to a single slit falls at 30 degree coincides with the first minimum for red light of wavelength C. Look at this diagram first. See, the central maxima which takes in maximum intensity is followed by secondary maxima and minima. So the first diffraction maximum is about halfway between the first and the second minima, and direction of secondary maxima are given by a sine theta equal to plus minus 2n plus 1 lambda by 2 into lambda 1. Now for the first one, n is equal to 1. So a sine theta is 3 by 2 lambda 1. Position of minima, a sine theta is equal to plus minus n lambda. For red light of wavelength, you have been given a sine theta is n lambda, n equal to 1. You divide equation 1 by equation 2. Equation 1 is what? Here. A sine theta equal to 3 by 2 lambda 1 and a sine theta equal to lambda, and you get the answer.